Well, dear students, let's start our next unit of electrochemistry, that is electrolysis. And see, this electrolysis has two aspects, qualitative and quantitative. For both the aspects, see, this is a non-spontaneous process, means delta G for this at given temperature and pressure, it is greater than 0, means it is a non-spontaneous process, right? For electrolysis you have to use what, DC current, not AC current. So DC source of energy is required for electrolysis, and the cell which is used for this electrolysis is called electrolytic cell, right? And here anode is positive terminal of the cell and cathode is negative terminal of the cell. Cathode is negative terminal of the cell, right? Although anode involves oxidation, this involves oxidation, and cathode involves the reduction, right? So in the electrolytic cell, this is different from galvanic cell. The only difference is that in galvanic cell, anode is negative and cathode is positive. And other features are same, means anode is responsible for oxidation and cathode is responsible for reduction. So these are some important points regarding this electrolytic cell and electrolysis. Remember, DC source of energy you have to use. You cannot use AC current for electrolysis, right? Because in AC current, see, frequency is changing every moment, so there is no electrolysis in the solution. Okay. Now let's consider first case, and through which we have to develop some idea about the electrolysis. Suppose that we have inert container, right? This is inert, and we have taken two electrodes, inert electrodes here, and provided this is the DC energy source. This is positive, this is negative. External battery is added here. This is positive and this is negative. Right here, suppose that we have taken molten magnesium chloride, molten MgCl, right? So obviously this molten MgCl2 have this Mg2 plus ions, and Cl negative ions. So Cl negative ions has to oxidize here. So this will move towards anode. This is anode here. And this has to be reduced Mg2 plus. So this will move towards cathode. So this will accept the electron. This will accept the electron and this will lose the electron. So electron will transport like this. So electron will transport from here to, I mean from anode to cathode, and here this electrode, electrode, inert electrode, this will provide the electron to the Mg2 plus, and this Mg2 plus will gradually deposit here. And see here this chlorine gas and this gas is, so gas evolved from this system. So now see, see how much potential, how much energy is required from outside to initiate. So minimum energy, what minimum energy is required to initiate this process? You can very easily calculate this. See, anode involves here, because molten, what is the purpose of here to take the molten magnesium chloride? The purpose is that this system is free from other ions like H plus or H2O or any other species should not be present here, so that we can easily, identify the ion which is going to be oxidized or going to be reduced. If you have taken this aqueous solution, then what will happen? Water is there, so there is a selective discharge of ions you have to analyze. But here there is no case of, only Mg2 plus is there and Cl minus is there. So what is the anode reaction here? The anode reaction is, and one more thing, we have taken here 1 molar concentration, right? So anode concentration, anode reaction is here 2Cl minus gives the Cl2 plus 2 electron. What is E naught for this? The E naught for this is what is 1 point Cl minus to Cl2 minus 1.36 volt. So the oxidation potential of this chloride ion here, see, this is oxidized to Cl2, this is minus 1.36 volt, and cathode reaction is Mg2 plus 2 electrons gives Mg solid. And what is E naught for this? The E naught for this is minus 2.36 volt, right? So reduction potential for this Mg2 plus, this is minus 2.36 volt, and oxidation potential for chloride ion, it is minus 1.36. Now you can add this reaction and get the complete cell reaction. So what you get? Mg2 plus 2Cl minus will give you the Mg solid plus Cl. 2 electrons cancel. Now what is the E naught cell for this? E naught cell for this is equal to E naught of anode plus E naught of cathode. So you will get minus 1.36 plus minus 2.36. So you will get 6, 6, 12, 3, 3, 6 and 7 and 2 and 1, 3. Minus 3.72 volt. So now see, E naught cell is negative, means the cell reaction is non-spontaneous, right? So what is E external is required? So here E external is required minimum. The minimum E external is required from your battery, that is minimum. This is required equal to 3.7 volt. So if your battery rating is 3.72 or more, or more, more, more than 3.7 volt, then this, electrolysis of magnesium chloride will start. So this is called decomposition potential. So the decomposition potential of MgCl2 is 3.72 volt. So this is the minimum potential. Decomposition potential is the minimum potential required to just initiate the electrolysis process. And if your battery is constantly providing this potential, so electrolysis will proceed. And if you provide this more than this thermodynamic potential, if you provide more than this, so what will happen? Rate of electrolysis will increase, because in the thermodynamics, minimum requirement is fulfilled, the reaction will proceed, and if you provide more energy than that, then this will increases the rate of the reaction. So dear students, for electrolysis of any molten salt by using inert electrodes, because you have to take extra care in this electrolysis, because your container should not be active, your electrodes are not active, because if they are active, then simultaneous process will start. So you have to rule out all those additional steps or simultaneous steps in the electrolysis. So decomposition potential, it is the minimum potential, right, which is required to initiate this process. So if someone is asked, okay, what is the minimum energy required? So you can calculate Gibbs energy, delta G is equal to minus NF E naught cell. So minus 2 and F, see, F 96500 multiplied by minus 3.72. So you will get 2 multiplied by 96500 multiplied by 3.72. So this is equal to 717,960 joules per mole. So this is equal to 717.96 kilojoules per mole. See what a huge amount this delta G is positive. So delta G is positive means it is non-spontaneous. So you have to provide this amount of energy from outside to carry out this electrolysis of this 1 mole of magnesium chloride. Okay, so this is the situation. Now I'm taking the situation to the aqueous medium. Now I'm taking aqueous medium. So before going into the detail of aqueous medium, first I will explain to you the electrolysis of water. So I am taking here electrolysis of water. Electrolysis of water. Right? So first try to understand what is the electrolysis of water. So inert electrode I am taking, inert electrode. And second point I am taking here, uh, neutral water. Neutral water. Neutral water means pH is equal to 7. pH is equal to 7 means H positive ions concentration is equal to 10 power minus 7 moles per liter. Everything is very clear. So can we use here, can we use E naught of H plus oblique H2 or uh, E naught for water, decomposition of water into O2 for explaining for explaining the electrolysis, right? So the answer is no. Answer is no. You cannot take this value because value of this because this value is defined at pH is equal to 0, means this is defined at what H, when the H positive ions concentration is 1 mole, strongly acidic medium, and here we have taken what, neutral water. So for this we have to have the value of E of H plus 2 H2 and E of H2O oblique H2O2, means reduction and oxidation. So when we are saying that okay, reduction of water, so basically reduction of H plus is taking place there, and oxidation of water means liberation of I2, oxidation of H2O. So first we have to write the half cell reactions at this pH. So you cannot use this E naught value. Now it is clear? Okay. Now half cell reactions, half cell reaction. So for the reduction of water H2O, H3O, you can write H3O plus 2 electron gives H2 gas plus H2O plus H2O, right? 2 H2O. And this is cathode reaction. Basically an alternative and simple reaction, all of you are knowing this. 2H plus 2 electrons gives H2 gas, right? And oxidation of water, so you can write oxidation of water to 3H2O gives O2 gas, half O2 gas, right? Half O2 gas plus 2H3O plus 2 electrons. 2 electrons. This is anode reaction. Anode reaction. Or basically all of you are writing this type of reaction. 2OH minus gives half O2 plus H2O plus 2 electrons. Plus 2 electrons, right? So these are the alternative and simple steps all of you are writing in electrolysis of water, right? Basically you are writing in this way, but the actual reaction is this. You can represent with this. Now you can add this. You can add this. So what you get? what you get? H2O gives H2 gas plus half O2 gas. And now you can add this. So you get what? 2H plus 2OH minus 2H2O, 2H2O and H2O cancel. So you will have one H2O in the left hand side and half O2 gas plus H2 gas. So this is the way of writing of anode and cathode reaction in the electrolysis of water. In the electrolysis of water. See, in both the cases, your final reaction is same. So basically, in electrolysis of water, at cathode, hydrogen gas is released, and at anode, oxygen gas is released. Right? See, hydrogen gas at cathode and oxygen gas at anode. Right? Now, see, cathode, E cathode. I'm taking one by one, right? So E of cathode is equal to E naught of cathode minus 0.0591 by 2 electrons to log. See, this is 1 atm H2O liquid, so this is 1 by concentration of H plus square. See, Q for this half reaction. This is H plus, so this is 0.00 minus 0.0591 by 2 log 1 by 10 power minus 7 square. So you can write this 0.0591 log 10 power minus 7. So this is equal to minus 7 into 0.0591. So this is equal to minus 0.414. Right? Now, anode reaction. What is anode reaction? So anode reaction is half O2 gas plus 2H3O plus 2 electron gives 3H2. So Q is equal to 1 by concentration of H plus square, right? So E of anode, I have taken reduction reaction. Here I have taken oxidation, written oxidation, but here I am taking reduction as a standard. E anode is equal to E naught of O2 oblique H2O minus 0.0591 by 2 log 1 by 10 power minus 7 square, right? So this value is 1.229 volt. You can take from table, E naught table. 1.229 plus 0.0591 log 10 power minus 7. So this is equal to 1.229 minus, this we have solved here, minus 0.414. This is equal to 0.815 volt, right? So delta E is equal to E naught cathode, E cathode minus E anode, and reduction on both, right? Reduction on both. So E naught cathode minus 0.414 minus E naught anode, reduction both, minus 0.815. So this is equal to minus 1.229, right? So it means the electrolysis of water is what? Non-spontaneous, and this decomposition potential for water at pH 7. So decomposition potential for water is decomposition potential for water is 1.229 volt, right? Clear? So in this way you can explain how the decomposition of water, how much potential is required for the decomposition of water, right? uh, in the electrolysis, right? In the electrolysis. Okay. Similarly, you can now you can make one generalization here, because at pH 7, at neutral water, for neutral water, and this is very important generalization, for neutral water, or not for neutral water, make the electrolysis of salts at pH is equal to 7. At pH is equal to 7. So there are two generalization I am deriving here. First is I species can be reduced. Species can be reduced if its reduction potential algebraically, if its reduction potential is algebraically algebraically greater than minus 0.414 volt, right? Minus 0.414 volt. And second generalization, I species A species can be oxidized only oxidized only if its reduction potential, I am explaining both in terms of reduction potential. If its reduction potential is algebraically smaller than is smaller than 0.815 volt. 815 volt. If not, suppose that if a species, if not, then water will reduce and water will oxidize. If not, then water will oxidize or water will reduce. Right? Now, see, suppose that a question is given, an aqueous NiCl2, aqueous. It is given 0.1 mole. Suppose that, because concentration also important, and under 1 atm pressure, 1 atm pressure, right? It is given. Find the species which gets oxidized and reduced at pH 7, at pH is equal to 7, and B at pH 0. So you have NiCl2 0.1 molar, right? So first you have to gather all the information for the first A, pH 7. pH is equal to 7 means concentration of H plus 10 to the power minus 7, right? So and you have ions Ni2 plus and H plus to be reduced, and oxidation, for oxidation you have Cl minus and you have water. These are the species to get oxidized. So basically here you have four couples, two different cells can be made, different cells can be made, right? Well, now see, we can compare this E naught value. E for this at pH 7. For these two species are we have to get reduced, and these two are to get oxidized. So for first I am taking cathode. So cathode, since we have calculated this for H plus in the above case at pH 7, so only Ni2 plus I have to consider. Ni2 plus 2 electron gives Ni, right? Gives Ni. Now E of Ni2 plus oblique Ni is equal to E naught of Ni2 plus oblique Ni minus 0.0591 by 2 log 1 by Ni2 plus concentration. I am considering this complete dissociation. So 0.1 molar. 0.1, right? 0.1. So this Ni2 plus to Ni is 0.23, 0.23 minus, and this is what, minus 0.0591 by 2, and log 10 is 1. So now I can directly write minus 0.26, minus 0.26 volt. Now compare. Now compare to this statement. A species can be reduced if its reduction potential is algebraically greater than minus 0.414. So see, E of Ni2 plus oblique Ni is equal to, we have calculated with this concentration, minus 0.026, which is algebraically greater than minus 0.414 volt, right? Volt. Thus, Ni2 plus preferentially discharge over cathode, right? So in this case, H plus will not discharge. Clear? Hopefully, all of you are clear in this. Similarly, now we can do for this oxidation. We have already calculated this for water. So if we compare this Cl minus, reduction of this Cl minus, so half Cl2 plus electron gives Cl minus. So Q is equal to concentration of Cl minus is NiCl2 is there, so this is 0.2, right? 0.2 in the solution, 0.2. Q is equal to 0.2. So E of Cl2 oblique Cl minus is equal to E naught of Cl2 oblique Cl minus is 1.36 volt minus 0.0591 by 1 log 0.2. So this will come to the 1.4 volt, right? 1.4 volt. So the E naught reduction for Cl2 oblique Cl minus is equal to 1.4 volt. And see here, a species can be oxidized only if its reduction potential is algebraically smaller than this. So is it smaller than 0.815 or greater than 0.815? So this is greater than, reduction potential is greater than 0.815 volt. So what will happen? So this water will discharge before this. So water, since it is greater than this 0.85, since it is greater than this, thus H2O will discharge at anode at anode, right? Water will discharge at anode. Now it is clear. If algebraically it is less than 0.815, then only this species will discharge, right? So in this way, you can what find that which species will preferentially discharge at which electrode, right? Hopefully all of you are clear. See, a species can be oxidized only if its reduction potential is algebraically smaller than 0.815, but here we are getting greater than 0.815 reduction potential. That's why I have designed for reduction equation. Thus water will discharge at anode, not Cl minus, right? So what is the final answer for this question, part A? The final answer is at anode uh, water will discharge. So what is the water oxidizes preference than Cl minus, and cathode nickel will Ni2 plus will reduces than H plus, right? So in this way you can compare. So what conclusion we can draw here, that the preferential discharge or what is the discharge potential in this case? So delta E is equal to E cathode minus E anode. So cathode we have calculated minus 0.26 minus 0.26 minus anode we have calculated 1.4. So this is equal to minus 1.4 1.66 volt. So this is the discharge potential. This is the discharge potential of nickel salt electrolysis at pH is equal to 7. So whenever you have more than one species to get oxidized or reduced in your system, then you have to check one by one. First you have to make the list, what are the species have ability to oxidize and what are the species have ability to reduce, and then compare one by one. And the statement I have given you, you can compare, right? You can compare with that. Now come to the next part of the question, second part of the question B, that is at pH is equal to 0. So at pH 0, I think there is no change in the reaction of cathode, because in cathode there is no involvement of H plus. So there is no change at pH 0, no change in the cathode reaction, right? So still for cathode you will have E of Ni2 plus oblique Ni E of Ni2 plus oblique Ni, this is equal to what? Minus 0.26 volt minus 0.26 volt, which is algebraically greater than minus 0.414 volt, right? This is for water. So I mean, what, don't write water, you should write H3O plus, right? So this will, I mean, discharge. So no change in the cathode reaction. Now what about anode reaction? Anode reaction, anode reaction. This time, see, your this ECl2 minus, because here see in this reaction there is no H plus, so concentration of nickel chloride is same. So I mean there is no change in this what I mean this condition. So E naught of Cl2 oblique Cl minus, E naught of Cl2 oblique Cl minus is equal to 1.4 volt. But this time your reference will change, because this is for when concentration of H plus is 10 power minus 7. But when this is concentration of H plus is what 1 molar, see here, see, when consider this is the equation. This value will come 0.815 when concentration of H plus is 10 power minus 7 molar. Now this is 1 molar. So 1 molar means this is 0. Now this is 0. So now this time you have to compare with 1.229. So when pH is equal to 0, then your hydrogen reference change, and this is 1.229 volt. And this is the for oxidation of water. For oxidation of water. So this time still it is greater than this, then again there is no change in the anode reaction as well. See, reduction potential of this is still more than this. Thus H2O will oxidize preferentially than Cl minus at anode. So your anode reaction is still not changed, but this time discharge potential will change. See, with change in I mean pH, your discharge potential will change. So E cathode minus E anode. So cathode minus 0.26 minus 1.229. This time this volt. So this is 9, 8, 4, 1.489 minus volt. So this time this is the discharge potential. So discharge potential is equal to 1.489 volt. So you have to provide this amount of energy from outside, right? So this is the discharge potential. So there is no change in the, preferential discharge of ions, but one property is changed, that how much energy is required to discharge that is changed, right? But in few cases you will find that in the electrolysis, due to this change in the concentration and change in the pH, electrode reactions are changed. So this is how to calculate the discharge potential, and what is the requirement for this electrolysis, how much energy is required from outside. Now you can evaluate in every case, right? So this is the concept.